Welcome to another unit of the ISM course on Statistics 2. This time with a unit on the binomial distribution. With the binomial distribution, well, I can directly mention that's like one side of the coin, and the other side would be the hypergeometric distribution. What's the link between the two distributions? Well, imagine you have a box with black and white balls inside, and you're randomly drawing one of the balls. And then the probability which you're interested in is, for example, you're drawing 5 balls. What the probability of having, let's say, 3 white balls or 4 black balls. The difference between binomial and hypergeometric distribution is that with the binomial distribution, you use this whenever after you've drawn one of the balls, you replace this in the box. With the hypergeometric distribution is you draw one of the balls, you take a look, white, black, and then you leave this outside of the box. Meaning, with the binomial distribution, the probability, being the relation of white and black balls, always remains the same. With the hypergeometric distribution, so without replacement, there the probability changes. The relation between white and black balls changes with each draw. That's the big difference. There's also how to know which of the two distributions is necessary. If you replace the balls after each draw, binomial. If you do not replace, hypergeometric. And here we're talking about replacement, about binomial distribution. With this we can switch to the probability density function. And the probability density function tells us the probability that when you randomly select, for example, n balls or n objects, that k will have the property you're interested in. So here in our example, which we will use for the whole unit, we draw n balls and we are interested in what is the probability that of the n balls, k will be black. We're going to write this in the following form. P of x equal to k. That's how many of the sample should have the property we're interested in. Then we have this density function here. And this consists of 3 parts. First, we have the last 2 parts, p to the power of k and 1 minus p to the power of n minus k. Well, if we work our way backwards, we have the last part. That's the probability that n minus k of the selected balls are not black. So that's the probability of this part of the sample which should not have the property we're interested in to occur. So the first part, that's exactly the opposite. That's the probability that k of the balls will have the property we are interested in, so will be black. So basically our sample consists of 2 parts. The part which will have the property we are interested in and the part which won't have the property we're interested in. The first probability, p to the power of k, that's the probability of the first part to occur, to have k balls with the property. And the second part, that's the probability of the second part occurring. So that's the probability of the balls which will not be black. And all of this we multiply with the n over k. That's, well, we can imagine if I have n objects, how many subsamples are possible which will have exactly k objects. Or in other words, how many possible samples exist with exactly k black balls? Well, if I have 5, I might imagine I can have black, 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 non-black, non-black. But I could have the exact opposite as well. Non-black, non-black, black, black, black. And different other ones as well. So I start with the n over k, possibilities of samples of size 5 with exactly k black balls times the probability of k balls being black and the probability of n minus k balls not being black. So the rest. Well, this might sound a bit complex. It becomes a bit more comprehensible if I will just illustrate this with an example. So here with the example we have, if Hans flies with a plane, there is a 5% chance that at the customs checkpoint he is randomly selected. In the last month, Hans took 6 flights. What is the probability that he is never checked by customs? First, we can note the different information this text gives us. So first off, there's this fixed probability of 5% of being selected. So our P, our probability here is 5%. We also know that we have a binomial distribution because these 5% are fixed. They don't change. That's an indicator for binomial distributions. We also know we're considering 6 flights. So the sample size is 6. And he should never be checked, so our k should be 0. So the event is being checked by customs. As I said, he goes through customs n times, should be checked 0 times. So k 0 and 6, and the probability of being checked 5%, 0.05. Then we recapitulate here this formula, and we have to insert all the values we just wrote down. So for n6, p 0.05, k 0. Then this looks as here. And well, this simplifies because 6 over 0, anything over 0 is always 1, times 0.05 to the power of 0, everything to the power of 0 is always 1. So we're only left with 1 minus 0.05 to the power of 6, and that's 0.95 to the power of 6, or 0.7351. So there's a 73.51% chance that he will never be checked by customs. Well, this makes this a little bit clearer what is actually happening here, how I can use this. So we can continue with the so-called cumulative density function. That's, well, the first part was about a specific amount of balls should be black or non-black. Or in other words, a specific amount of events, of objects, should be in the sample. Here, we're going with a bit more flexible way with saying at least or at most this much should be part of the sample. So in other words, I could write this as the probability that at most k balls out of n balls are black. Then it looks as follows. So it should be x being lesser or equal to k. Then could be 0 balls, could be 1 ball, 2 balls, 3 balls, but at most k balls. And this just means we're calculating all probabilities from 0 till k. And then we add all of this up. The same thing is done if we have the formulation that probability of at least k balls out of n balls being black. This looks the exact opposite, so it's x greater or equal to k, meaning we start at k, and then we go upwards till the end of the sample. Well, here sample size is n, so we start at k, and we go up to n. And again, we're calculating all the different probabilities for each of the different cases, one after another after another. Well, this could be quite a lot of work. And for this, there's an easy way to shorten this down. Well, there are some easy ways, but there's one way I want to mention here. This is, if I just recall, that the maximum probability is 1. And well, the opposite from lesser or equal to is greater than. So I can rewrite lesser or equal to k as 1 minus and then probability of x larger than k. Or the exact opposite way, greater or equal to k can be rewritten as 1 minus probability of x being smaller than k. This can make this easier relatively often. You can see this in an example. Here again we have, if Hans flies with a plane, 5% chance that the customs checkpoint is randomly selected. If in the last month Hans again took 6 flights, what is the probability that he is checked at least once by customs? So checked once, twice, 3 times, 4 times, 5 times, 6 times. That's a lot of probabilities to calculate. So again, we have the same numbers as before, except for the k, which here is 1. And we are asked about the probability of x being larger or equal to 1. As I said, this would mean we have to calculate the probability equal to 1, equal to 2, equal to 3, equal to 4, equal to 5, equal to 6. So we would have a lot of work to do. We can make this easier if you just go and turn this around. So instead of greater or equal to 1, we have 1 minus the probability of x lesser than 1. And well, lesser than 1, this translates into equal to 0, because there's only one number which is lesser than 1, and that's 0. So basically we have, in this case, only one probability to calculate. Well, the easy part is we already did this stuff, because this was the example before. However, I again inserted this here in the probability density function. This again reduces to 0.95 to the power of 6. This is the result from 2 slides back, and gives me a final result of 0.2649. So there's a chance of 26.49% that he's checked at least once by customs. And well, that's then all there is to this part. So there's only one aspect left to go with, and that's calculating the mean or the expected value and the variance for anything which is binomially distributed. And here we have the following 2 formulas. Well, the mean, the expected value, is relatively self-explanatory. We also see this from the example. With the example we have here, if Hans flies a plane, 5% chance, customs checkpoint, blah, blah, blah. In the last month, Hans took 40 flights. How often has he most likely been controlled by customs? Most likely, that's usually an indicator for expected value. So here we just take the sample size, 40 flights, multiply this with the probability, 5%. That's the 2 values here. We get our expected value, as I said, sample size times probability, giving us here number 2, meaning he's most likely been controlled twice during his 40 flights. If the whole process works randomly, that is. And well, that then is all I wanted to talk about in this unit. So I hope you enjoyed listening to it. I hope you learned something from it. And if you're interested in seeing more of this type of videos, learn more about statistics too, feel free to visit the rest of the course or have a look in the corresponding playlist. I say goodbye and see you next time.